I'm very happy to be here at CEMRACS and to give this talk. The title was just, I was thinking about talking about this complex geometries and realistic geometries in computational plasma. It's really large. So I will talk about kinetic problems, also MHD, even if the focus of my work is on MHD. So this work starts when I was during my PhD, and Alexandre, my PhD advisor, asked me to find a new numerical scheme, a new numerical method to handle complex geometries for the quasi-neutral equation. So we end up with this isogeometric analysis that has been developed by Hughes, and then we apply it in many problems in plasma physics. So here is somehow a cocktail of what we have done before and what we are doing now. Okay, so we'll start by the motivation of this work. I will talk a little bit about B-splines, NURBS, curves, and surface as CAD tools. Then I will present the isogeometric approach. I will give some applications and talk a little bit about this new refinement strategy, which is called the key refinement. Then we will talk about adaptive meshes, including the alignments and the equidistribution meshes. Okay, so let's start with the motivation of this work. So I'm working on DrawAkiza, which is a finite element code for nonlinear reduced MHD, and the aim of it is to simulate age-localized modes, which are MHD instabilities that are destabilized by pressure and current in H mode, and may lead to a loss of energy of up to 10%, and even in ITER we say that we expect a loss of 20%. Okay, so for physicists, they need to control the ELMs, essentially in ITER, and this needs a good understanding of the physics of ELMs, but also numerical tools in order to do this simulation. So there are a lot of challenging things in ITER, like the high anisotropy, the geometry also. And also there are a lot of computer science issues. So DrawAkiza was written in order to make simulation for ELMs, for ballooning modes, for disruptions, like this vertical displacement of the plasma. And now we have some control techniques like RMPs in order to control these ELMs, this age-localized modes and stabilities. So DrawAkiza is a finite element code that uses flux-aligned poloidal grid in the poloidal plane. It is based on what we call an isoparametric approach, which means that the elements approaching the geometry are used to approach the unknown. Okay, and then we have Fourier series and the toroidal direction. For the time stepping, we have a fully implicit Crank-Nicolson. Our matrices are usually of 10 to 7 degrees of freedom, and a typical run over 200 to 1,050 or 1,500 processors. So at the AFM, we use 7 million CPU hours a year, and the typical simulation, especially for JET, is about 100,000 CPU hour. Okay, so here are some limitations of the current version of DrawAkiza. One of the problems is this geometry. At the moment, the grid generation is done. It's not automatic, and it is done locally. So we have to stick all these elements together. I forgot to say that we use Bezier surfaces here in the poloidal grid. And this Bezier surfaces, as you can see here, can be stick together in order to have a C1 global surface. So this is the game. The game is how to create meshes that are C1, and so that our solution will be also C1. So there is this problem with the grid generation. There's also another problem which is about the exact geometry. We don't have the exact geometry, especially for example, the diverter. And also there are a lot of problems, including the boundary conditions. Nobody knows what boundary condition can we put on MHD, on real simulations. So for the numerical schemes, there are a lot of problems, including this memory limitation for realistic ITER simulations. So one of the solutions is to use higher order than the cubic splines, than the cubic Bezier, so that we can reduce the size of the discrete matrices. We can do this also by using higher regular elements. So we will not use only C1 elements, but also C2 or C3, depending on the degree of our basis. We have noticed before when we worked on Maxwell equation that the use of these higher regular elements leads to better CFL numbers. So maybe if we use higher regular elements, we can reduce the memory consumption and by the same time having large time steps. And then finally, we would like also to be able to derive some fast solvers or preconditioners, and for this we need to understand the algebraic structure of our basis. Okay, so here are some examples of the problems that we have with the current grid. It's mainly a polar grid, and we don't see it here, but maybe here. So you see here, it is like a polar grid, and then you have this problem at the center. Here the meshes are getting bigger, so there's a lot of problems here, and my work was to find a new way, an automatic way to describe the geometry and to define also the exact geometry. Okay, so let's start with my talk. So my work is really to use this CAD tools. So CAD stands for computer-aided design, and in this community there were a lot of very interesting work that have been done before, including fast algorithms, and especially in 3D animation industry, including medical one. There's a huge literature and a huge number of numerical methods that exist, but up to the work of Hughes, there was no link between the numerical simulations community and the CAD community. So he made the link between these two communities by using this isogeometric analysis approach. And his idea is that was to have the same description of the geometry and the unknown that describes that solves our PDEs. And so in this case, the functions that are our basis functions can describe exactly the geometry. Okay, so in this way, the isogeometric analysis contains also the isoparametric approach. But we also have seen the emergence of this key refinement strategy, which means that we can control the regularity of our solution. So how does it work? Well, let's start with some basic things that we have in DrawAkiza. So for DrawAkiza, as I said, we have to create the mesh locally by ensuring that we have the C1 constraint. Sometimes we may make this constraint weak and we only ask for a G1 condition. This is for people who use CAD. And there is also another problem, is that when you cannot force the alignment and want to be exact on the geometry, And at the same time, if you do M simulation during the nonlinear stage, there's no need to be aligned to the flux line. So you have this structure that goes around, and maybe if you use something that fits well the information that you have there, it will be better than just being aligned. So we'll see how we can mix the two of these two strategies. So we want to create a global mapping. So I will explain this, and be able also to choose either we want to be aligned to the flux surfaces, or to have like an equidistribution property. So for this we will use tools from tools from CAD. But in this case, we will not just focus on Bezier surfaces, because Bezier surfaces are just a very simple example of tools that you can find in CAD. So this work is based on B-splines in their general form. It also uses NURBS, even if I don't really like NURBS, because you end up with this rational fraction polynomials, and you lose one of my favorite properties of splines, which is an algebraic property, which says that when you derive a spline, it's just the difference of two splines of low order. And this is very interesting because it's like doing finite differences on the B-splines coefficients. So the basic idea of this isogeometric approach is to construct a mapping that maps what we call a patch. It's a logical match. It's just it can be, for example, just a unit square. So it maps a unit square onto the physical domain. Okay. So all your work will, for example, in your code, you'll have this metric that is given by this mapping. And you have to compute all this Jacobian and derivatives. So, okay. So a B-spline is a polynomial with the smallest supports possible when you try to ensure some regularity conditions. And for this, in order to create a family of B-splines of order k, you need to have n plus k points that we call knots. So t is the knot vector. Then if you want to create a curve, you need to have what we call the control polygon. And the control polygon is just a sequence of what we call the control points. So then you affect each one of these B-splines functions with control points using just the linear sum here. So this is a parametric curve, which means that you go from the interval 0, 1, in this example, for example, we go from 0 here, 3/4, and then 1 here. So we go from 0, 1 to R2, okay? So this is the same thing here. And here I plotted the basis function, and as you can see, they're not the same. So we don't have the same function everywhere. It's not like in the classical finite elements method when you have just a set of basis function and you have this function everywhere. Here it's not the case. You see that, for example, this function is regular. All these functions are regular except this one. Okay? And I can control the regularity of this function by adding by having higher multiplicity here. Okay, so the highest multiplicity that I can put here is equal to the degree of the spline. So here we have a quadratic B-spline, and with what we call an open knot vector. So the first and the last knots are equal. The multiplicity is equal to p plus 1, and then you can put inside the knots that you want. So here another example with, in this case, this knot vector, and you see that now we have something that we know This is just the Bernstein polynomials. So the same thing over all these elements. And this can be done by repeating all internal knots. So this is how we can control the regularity of our basis function just by repeating a knot. There are very interesting properties of B-splines. One of them is, for example, how we derive a B-spline. So if you take just the derivative of a B-spline curve, it's also a B-spline curve. And then you can access directly to the derivative at the extremities of the curve using the two successive control points. So the tangent of the curve is supported by the line P1, P2, and at the other extremity, it's supported by the line Pn minus 1, Pn. You have also the same results for the second derivative using the control points. And so, as you can see, we can stick together B-spline curves, and for example, to ensure C1 condition or C2 condition, and this leads just to some linear constants like this. Okay, so B-splines are polynomials of degree equal to the order minus 1. They are polynomials with the smallest support for what we call the Schoenberg space. They have also linear independence, partition of unity, which is very important for the completeness of our finite element space. Okay. So then, when we want to do some isogeometric analysis, we need to use what we call the fundamental geometric operation. So once you have created your mapping from a square or from the line 0, 1 to a curve, then you can refine this description. You refine it by inserting new knots, and this can be done by the de Boer algorithm or Blossoming algorithm. A lot of algorithms exist. You can also elevate the degree of your description, and you do this, and you keep, and the geometry is kept exact. There's no change here. We just change the description of how the mapping is computed, but the mapping is really kept exact. So then you can do the same thing for, you can define the B-splines for multivariate using a tensor product splines, so in a higher dimension. And so finally we get this refinement strategies. So we have the classical one, like the H refinement. It's just by inserting new knots. So you have really the equivalent of the mesh refinement in classical finite elements method. You have also the P refinement by elevating the B-spline degree. So this is the same thing as using higher finite elements, although in classical finite element codes. And then you have this new one, which is the K refinement by increasing or decreasing the multiplicity of our knots. Okay, so this will lead to a higher regular or low regular basis function. So the K refinement is really the strategy that is new in this work, and also the fact that we conserve the geometry exact. So in order to do isogeometric analysis, you start by a description of the mapping. This will give you what I call the coarse description. And then from this coarse description, which gives you the minimal degree of the basis and also some internal knots, then you can do this HP key refinements, which will keep the mapping unchanged. And this is why the Hughes call this method isogeometric. So here is an example. We have the patch with 4 cells and our mapping onto the physical domain, and then we refine in this direction, and we keep this geometry exact. Okay, for application, we started this isogeometric approach by applying it to the quasi-neutral equation, which is just the Poisson equation in the gyrokinetic setting. We derived a fast solver in this case, which beat for example, the super LU solver. We had some performance like 2000, a speed up of 2000, depending on the degrees of finite element that we use. We have also applied to MHD equilibrium to solve the Grad-Shafranov equation. So more generally, we have a code which treats any kind of PDEs. It's a generic PDE solver, and we have also done the work for Maxwell equation. And in this case, we used what we call the discrete sequence of de Rham based on these splines. And this work was done by Annalisa Buffa. So she derived the discrete sequence in this case, which is just like if we use Nedelec elements, but with B splines. And then we applied also to semi-Lagrangian schemes. So I call also semi-Lagrangian scheme like a particle method. So when you use particle methods, you have the choice, because you have two things that you need to compute: the velocities and the position. So you have the choice: either you compute everything on the physical domain, or you compute it on the logical domain, or you do some mix between them. So this was a project for the CEMRACS of 2010, I think, or 2011. And we used a similar Lagrangian scheme, but on the physical domain. So the result was not quite good because the time conception was very high. We have done the same thing for peak code, but in this time we wrote everything in the parametric domain. And that was very difficult to write the motion equations. So at the end, I end up with a new method, and now it's we have implemented in Celalib. So it is what we call a hybrid semi-Lagrangian scheme, where you compute the position in the logical mesh and the velocity in the physical domain. And with this, you don't need to invert the mapping, and everything is really fine. So Aurore will present this, I think, next week. So I skip this part and leave her the privilege to do it. Okay, so then we have done some work on reduced MHD using this isogeometric approach, and now I'm working really on mesh generation, including alignment procedure, but also anisotropic, what I call anisotropic adaptive mappings, and you'll see what does it mean. What does this mean? Just at the end of the talk. So we have derived also geometric multigrade solvers, especially for nonlinear solver. Okay, so let's talk a little bit about the ski refinement strategy. So is it really a blessed strategy? Well, if you read what is written here, you'll say, well, ski refinement is the best thing that you can do, but I forgot to do something. Okay, so in this example, I compare the solution of the Poisson's equation using the B-splines of degree P with the minimal regularity, which is C0, and the maximal regularity, which is CP minus 1. Okay, so if you take P equal to 2 or 3, so quadratic, cubic, and cantic splines here, you have the numbers of degrees of freedom, which is quite stable. Here it goes like a multiple of 8. The number of non-zero of your matrix is, in this case, multiplied by 10 in this case. So here the time conception for super LU. So you see that the time is the difference is very important, and also for the conjugate gradient. So here my point was, I want to compare for the same accuracy, what is the best regularity? Is there any difference between using higher degrees, higher regular elements, or lower regular elements? And for the same accuracy, equivalent accuracy, we see that the time conception for regular elements is better than the C01. But we need to do memory conception, especially for the LU solver, to see what is the difference between the two of them. But as you can see, the numbers of degrees of freedom is very high here, so we can expect that even the memory conception is better or equivalent in the case of higher regular elements. Okay, so now we'll talk much more about alignment and equidistribution. So as I said earlier, my work is on Elm simulation, and what DrawAkiza do is is to start with a flex aligned grid, which is fixed once for all, and then we use this grid. And for example, when we have elms, we have this structure like this. As you can see, well, the meshes here are bigger than at the inside of the plasma, and so we lose accuracy here. Otherwise, we have to refine to have very refined mesh in this part. But this leads to bigger systems, and this is what we want to avoid in this work. So one of the strategies is to say, well, we can try to do alignments everywhere, but here we can do something else which will make our cell size small when for example, the gradient of the density is very high. So is there any possibility to create such mappings that will adapt the shape and the size of the mesh depending on a given function? This is what we call a monitor function. And the idea beyond that is really to use this this structure and these properties of the control points. So by moving the control points, I can change the shape of the geometry, and this is really what it's like in video games. It's like also in animation movies. It's just they move some control points, and you see the face changing. So this is really the idea. We move the control points in order to have better resolution in high density region. So for this, we need to define a strategy. One of these strategies is to use an iterative method by a minimization of an estimation of the numerical error. So this is very difficult in MHD. We will see an example for elliptic problems. It's very fine. You can derive the a posteriori estimates and then use it as an estimation to compute the good mesh. But it's very difficult to do it in nonlinear problems or even in MHD. So then we found another strategy to do it by using this equidistribution property. And as I said, this needs a monitor function. And but this strategy needs to the resolution of the Monge-Kantorovich optimization problem, which leads to the Monge-Ampère equation. Okay, so the most important question here is: are these strategies compatible with the injectivity property? Because my aim is to construct a mapping from square to a physical domain. So this mapping must be injective. And there is no reason for an optimization method to ensure this injectivity property. Okay, so the first basic idea is to say, well, I have this the magnetic fields line as described by the IFIT code. It's an equilibrium code that takes into account the coils and everything. So this is the configuration of the plasma. So you have inputs like this. You have the wall of ITER in red, and you say, well, is it possible to create a set of mappings that maps a number of squares onto parts of this domain. So this means that we have to cut this this geometry. Like for example, say we have this closed magnetic fields lines with this closed surfaces. We have this open surfaces. Well, so we'll take the inside as a subdomain, and then take the other one, and so on. So you'll see a description with 6 patches just after that. And the idea is to say, well, we have these lines. We take, for example, in our case, we can take the UK as we have to fix what we call the parameterization and create a B-spline family. So this is the assumption that we have. The parameterization can be whatever you want, but the choice of the parameterization has an impact on the mapping that you will create. And then you need to solve this. You need to find the mapping by minimizing a functional which can be written like G0 plus lambda G1, where G1 is something that will regularize the surface, and in fact it is just an approximation of the curvature, and such problem is known as the optimization with fairing. And one of approximation that you can use for G1 is what we call the thin plate approximation, and this leads to the B-Laplacian in your when you use the when you try to solve this with the linear system. So this construction does not lead to injectivity, and you need a lot of parameters to do it, but it's quite easy to have it. So here are some impacts of this parameterization. Just by changing the values of the points u, we can change for example, you see here, this is not the same. And even if I change, so these 2 cases are for an optimal value of lambda that we can compute. And this one is for a bad value of lambda. And as you can see, we don't match the whole given points. And in order to match the boundary, you have to set boundary condition on it. It's very easy to do it with B-splines. But I just want to show the impact of the parameters that we have in this method. So this is, for example, a construction of ITER by just splitting the geometry into 6 regions, and as you can see here, the connectivity of all these patches. So you see here the patch F, which is in white inside. I left this whole for a reason. This is just to avoid the center problem that we had before, because in our case I can change the description inside the plasma. Okay, so this is the first patch, which corresponds to closed magnetic surfaces, and then you have this pink one. Okay, and so the 2 patches have the same edge here. So, and the edge is just this curve. Okay, and then you have the patch, the red one and the green one, and you see that this point here is the same as here, and it corresponds to the X point. Okay. Yes. You can try to have a corresponding construction. This was just for one single X point, but you can try to do it. Even if I have another example just after that, which is on west, and in this case we have two X points, but this one is not inside the plasma. It's not inside the domain, our computational domain, so it's not a problem. to have it. We have to figure out a new decomposition of the domain. but this can be done easily. And once you do it, it's in the code that I have developed. There is an automatic way of saving what you do, and then it generates the corresponding Python scripts. So you don't just do it once, and it will do it for you every time. And so, for example, here this is the construction for West, and we use CAD algorithms to compute the intersection of our magnetic fields line with the boundary, which with the wall here. Okay, it's quite weird, like a wall, but. And then we have an algorithms which based on the key-means algorithm that find the best magnetic surface that ensure you to have the biggest area here, because this is what we are interested in, because the heat flux will be in this on the diverter here. Okay, and then you can compute the corresponding mesh. So this is, in this case, I have done the decomposition with many patches, and this is automatic, and we have the alignment requirement here inside. So I took this this description in order to say that I want to change the mesh strategy here, because here we have the X point, and I don't want my lines to go through the X points, so I want something else, and this is the topic of the next part. So, but here we will be aligned at what I call the external patch here. We will be aligned here also, but here will be adaptive. Okay, so let's start with a very basic example on an elliptic problem. So this work has been done by Bernard Morin and Q. And so they start by deriving the a posteriori estimates, and you have this inequality here. So by knowing the numerical solution, you have access to the error that you are making on your analytical solution. So the idea is to change the control points, to move the control points in order to minimize this quantity and then this one. Okay, so this is based on an optimization problem by searching for the good gradient and then finding the good way, the good path that minimize the error. The problem is that it takes a lot of time to do. The cost is very expensive, and there is no reason to preserve the injectivity. So here is a very simple example. Let's take just a square with this description, and then if you take, for example, a solution of like sinus 2px to sinus 2py, you have, or just let's take just a hat function here. You say that we need to move the control points inside the domain in order to reduce the error. Okay, this is what we call the refinement strategy. So in order to preserve the injectivity, we need to add nonlinear constraints, and this becomes very, very difficult. So another way to do it is to solve what we call the Monge-Kontorovich problem. And the problem of the Monge-Kontorovich is, well, it goes back to Monge, and the problem was you have some holes and you have some sands. What is the best way to transport sands and to recover all holes? This is the problem. And if you see this in our example, you can imagine that the holes are our meshes, and the sands are just this information that you have, for example, the error, and you want to dispatch the error over all these holes. So, as I said, we will start by by this sand, and the sand for us will be what we call a density, or a mass, or a monitor function. Okay, so you have two densities, even if one of them will be just one. The second one is really the quantity that you want to equidistribute over your mesh. And then the problem that you need to solve is an optimal transport problem, and you need to minimize this functional here. So the unknown here is the mapping psi, and in my setting, my real unknowns are the control points. Okay, so you can write this thing nicely, and then end up with this problem, with this equation, which is the Monge-Ampère equation. So you have to add the corresponding boundary conditions for this. And we have some theoretical results on the existence of the solution done by Brenier some time ago. And there are mainly two important things here. I think that the most important is the fact that the solution is convex. So our numerical scheme must somehow ensure that the function is convex, which is not easy to do. And then the solution is a solution. The unknown is a solution of the Monge control, and this is the ACN of our phi. So our phi is, in fact, the mapping will be written as a gradient of a function psi, of function phi, and this function must be convex here. Okay, so you add the boundary condition, and then you can solve this thing using the method that you want. A huge literature has been done, especially by Dean. Our work was motivated by the one by Delzano. They use an iterative Newton-Crillon solver with preconditioning and finite difference, and you'll see that in our case it's very different. There's also the work by Awanu, who's using triangular real splines, so he can treat complex geometries. Another approach also is to consider the Monge-Ampère problem as the steady state of a parabolic equation, which is the parabolic Monge-Ampère equation. So you have two versions here, the one by Budd and Williams and the other by Sulman. So we propose to use the method developed by Benamou, Froese, Obermann, and use the isogeometric analysis setting. Okay, so the numerical scheme that we use is to, rather than solve directly the equation with the Hessian, we solve, in fact, a nonlinear problem by inverting this operator here. And there is a result that says if the solution is in H2, then it's a fixed point of this operator. Okay, so you can start with any initial value and compute the new value by just inverting the Poisson operator, the Laplacian operator. So there are many advantages for this approach, especially the fact that I prefer to work with Laplacians, because we can derive fast solvers for Laplacians. You can have fast, nice algorithms like multigrade algorithms, or as I said, fast solvers using the Kronecker product. Yes, so this is what I like in Poisson. So this is just how we can construct the multigrade algorithm, and as I said, you can refine a B-spline curve or surface by inserting new knots, and in fact, doing this is just like multiplying your control points by a matrix. So if you insert a new knot, you multiply the control point that you have by a given matrix, and this leads to the new control points. So if, in this example, we insert a lot of knots, then the resultant matrix is just the product of all these matrices. This is for 1D. In 2D, one approximation for the interpolation operator is to take the Kronecker product for these two matrices that goes from a lower level, a coarse level, to a finesse level. I don't know if you know what I'm talking about here. So in multigrade algorithms, you need to specify what we call the interpolation operator and the reduction operator. And the multigrade algorithm is to solve. So in order, for example, to solve let's say the Poisson equation on a fine grid, let's say that you have here your domain with this mesh, and in order to solve the problem on this mesh, we use some iterative solver like Gauss-Seidel, which has this smoothing operator property, and then we make some loops, some iteration in the finesse grid. We get the error. We send it to a coarse grid. Then we repeat the same thing, and we get again the solution, the error here, and we continue. So this is a V cycle. You can imagine that you have something like this, where it's not a good example, but and then you can end up with a W cycle. So this means that you go from the thinnest level here. You can go, for example, to so let's say this is level n. This is level n-1, level n-2. Okay, so you go from level n to a level n-2, and then you can go, for example, to level n-1, and again, something like this, and do the path that you want. And all these things are done thanks to these operators that we call the reduction and the interpolation. This is how you transport a B-spline or your object from your discrete space, from a given discrete space, to another one. Okay. So here are some results for a domain with the Nix point on an anisotropic diffusion problem. And as we can see here, if we take we have two choices: either use the multigrade as a solver directly, or we use it to accelerate geometries, for example. And this is what we call the precondition as a preconditioner, in fact. Okay. So as you can see here, we can reduce the number of iterations to an order of 10, here depending on the anisotropy factor. Okay, so again, this was for the square domain. This is for the X-point domain with the 128 points in each direction. And then we have here a comparison between this geometric multigrade and the conjugate gradient in Petit. In Petit, yes, using two processors, I think. And so you can see that for the square, the geometric multigrade beats Petit. Okay, so here is for the X point. For the X point, it's not quite good because the interpolation operator that we use is not a good approximation. You've seen that I've just take the Kronecker product of the two matrices into the direction, and so I don't have any information about the volumes that I have inside my domain. So we have to construct the interpolation operator with a different way. Okay. So the idea, so in order to solve the Monge-Ampère equation, we use a multigrid strategy, but for nonlinear problems. So we solve the Monge ampere equation on a coarse grid in order to find a guess solution then that we will transport to the finest grid, and by using the matrix that I showed you before. So by doing this, you can divide the time for your solver by 2, and it's very easy to do it. Okay, so this is just for validation. We get the good convergence order for quadratic, for cubic, and for quartic B-splines. And here the number of iteration of our Newton solver. Okay, so here are the meshes that you can get with this procedure. You take this monitor function, you put it inside the code, and it will give you something like this. So remember that we are still working on structural grid. So this is just the image of my square, but my control points were moved in order to make the ratio between the norm here, the information that you have here, with by the size of the mesh here, of the same magnitude. Okay. We have another example by moving this spot. You can do it also. Here we have time consumption. We can talk about it later, but we have very promising results compared to the one that people have done before. But the most important example is this one with the vortex. So you can see that we get the right deformation of our monitor function. So here are the results for this example, and as you can see, if we, depending on the B-spline degree, depending on the precision that you want, you will get a CPU time that is higher or lower. So you have to choose and to pick up the one that you want. One thing which is very important is that so here is an example for the circle also. You see that we get the anisotropic mesh here. I made some comparison with the work of Delzano. So in our method, we solve the direct problem, which means that we solve really. We try to find the phi such that psi is equal to gradient phi. In Delzano, they solve the inverse problem. Why? Because the inverse problem is much more stable. But by solving the inverse problem means that they solve for psi minus 1. But the problem with the inverse problem is that you need at the end of the day, you need to invert everything to get the direct one, and they don't give this time consumption in their article. So there is only the inverse problem, and you can do anything with this. So their work is based on Jacobian-free Newton-Krylov using preconditional multigrade. There are a lot of parameters there are parameters that you need to use for GF and K. But in our method, there is no parameter. It's free from parameters. You have the regularity that you want for the mapping because you set it. And then the final map is known everywhere. But for the other works, the mapping is known only on the grid, on the discrete grid, on the points that you specified for your grid. So, and then you can use HP refinements strategy to keep the mapping unchanged. Okay, so we may finish here. So my work is based on some tools that I have developed. It's the PKZ suite, where you have the CAD modeling tool here. It's called CAID. You have a lot of models that are already implemented. You only need to import them and to use them. It's an oriented object code. So you can do a lot of nice things. It's also parallelized, and but there's still some work to do. So Pegasus is this guy. I don't know if you know the story of Pegasus. So it was, yeah, just read it and tell me. Okay, so we can finish this talk by thank you for hearing me.